Okay, so now we're going to look at the example. So this is question 6. And we want to find the cosine and sine series for the function f of x is equal to x. So we want f of x is equal to x, and this is going to be on the interval 0 to pi. So 0 to pi. Okay, so again, I'm not going to compute these coefficients. I want you guys to compute them on your own. And again, it's not so much the computation of the coefficients that I'm primarily concerned with. I'm concerned with, given a function, how can we know what its sine and cosine series are going to look like? In general, what its sine and cosine series looks like on all of R, but in particular, just on the interval 0 to pi or 0 to L or 0 to whatever that we care about. So if I look at the sine coefficients, vk is equal to 2 times minus 1 to the power of k plus 1 over k. And if I look at the cosine coefficients, ak is going to be equal to minus 4 over k squared pi, and this is when k is odd, and it's equal to 0 when k is even. Okay, I'm going to pause it. I wanted to do that in purple, so I'm going to pause it, and hopefully I'll do everything correctly, and the next thing you'll see will be something like that, but in purple. Okay. All right, I wanted to do purple just to keep the colors the same or consistent. All right, so let's look at doing something like we did before, where we're going to sketch the graph. All right, so let's look at. And we're going to start just from looking 0 to pi. Now my function is f of x is equal to x, so it's going to be something like this. Now let's look at the sine series. The best case scenario for the sine series is that, well, it's going to be equal to 0 here, which is what the function is, so that's okay. And it's going to follow, it's going to be equal to the function like this. Again, the dashed blue line is supposed to be on top of the black line. Let me just make sure that, yes, the dashed blue line is supposed to be on top of the black line. Of course, at pi, though, the Fourier sine series is going to be equal to 0. So this is the best that we can hope for the sine function. Okay, and now let's try using this, and this is actually what we are going to get. So using this, let's see if we can also determine what the series is going to be from minus pi to pi, or from minus pi to 0. So if I look at minus pi, well, what is the odd? So this is f of x is equal to x from 0 to pi. The odd extension of that function is just going to be x going this way. So it'll be like this. Similarly, in minus pi, it's going to be equal to 0 because the sine functions are also 0. If L is equal to pi, you plug in minus pi for x, you're going to get, if L is equal to pi, the pi's cancel, so you get sine of k times minus pi, which is 0. Okay, and then now if we want to look outside of the interval minus pi to pi, we're just going to take this graph and copy and paste it. So let's say this is 3 pi, and this will be 4 pi. We'll have something that looks roughly like this. The tip is that you should draw the intercept after you draw the line rather than before. Okay, so then this would be filled in here. So this would be 2 pi, and this would be equal to 3 pi. Okay, and then over here we would have something like this. I didn't draw the axis over far enough, so let me do that now. So this would be, this point here would be minus 2 pi, and this point would be minus 3 pi. And again, we call this the odd periodic extension of our function. Odd because it's odd from minus pi to pi, and periodic because we're just copying and pasting it. Though clearly I didn't do a great job with the copying and pasting. These are all 45-degree angle lines. Okay, so let's look at the cosine series. Now for the cosine series doesn't satisfy the same boundary conditions. Okay, the derivative of the cosine series is what satisfies the boundary conditions, but the cosine functions don't satisfy the boundary conditions. So then it's possible, the best case scenario here is just that for the cosine functions, they're just actually equal. So something like this. So there's a purple line on top of the black line. Again, they should be all, like, they're all the same line. I just clearly can't draw them all on top of each other. Okay, so now let's do the same thing. Let's do the extension of this. Well, if I do the extension from minus pi to pi, and when I say extension, I mean I'm going to take this formula. So where did this formula come from? We derived it by only sampling the function from 0 to pi. Just like for the sine functions, we only sampled from 0 to pi. But why can't I plug in a number from minus pi to 0 here? And the answer is there's no reason that I can't do that. I can. And so I want to get, if I know that this is what the graph looks like from 0 to pi, what does it look like if I plug in a number from minus pi to 0? Since the cosine functions are even, whatever I get has to be even. And so it's just going to be the even reflection, in other words, reflecting across the y-axis, and we're going to get something like this. Okay, and so now, if I want to extend this to the whole real line, I'm just going to take this and copy and paste it. So I'm going to take this point here that's at 0 and just pick this whole graph up, this whole V shape up, and plop it down right there. And so it'll look like this. Except for the purple guys, it's actually going to be filled in there. Something like this. Okay, so what this illustrates, and I'll show you in Desmos, I'll put this on Desmos in just a moment and talk about it. So what this illustrates is that the Fourier sine series for this function is equal to the function at every point except for pi, and the Fourier cosine series is equal to the function at every point from 0 to pi. Okay, and let me just point something out. If I'm just looking at the Fourier sine series, notice that it is, if I look, so if I forget about sine series at all, and I just look at my function from 0 to pi, and I take the odd periodic extension, notice that the sine series fails to converge to the function exactly at the points where the periodic extension is discontinuous. Again, in other words, it doesn't converge there, it doesn't converge there, it doesn't converge there, it doesn't converge there. Okay, the Fourier sine series fails to converge to the function at the point where the odd periodic extension is discontinuous. Even more so, at those points where it's discontinuous, what the sine series is equal to is the average value. Okay, so I want you, if you didn't understand what I just said, play it back and make sure that you understand it, because this is going to be the theorem that we show later on. Okay, and similarly for the cosine functions, notice that the cosine, the even periodic extension of the cosine functions are continuous everywhere, and the cosine functions converge to it everywhere. Okay, so let's look at Desmos. My pictures. If you're interested, what my office looks like, these are my pictures. This is just to let people know that I have friends and family. I'm just showing off. It's interesting, though. These pictures here have our two older kids. Our older son is now 2 years old. There's no pictures of him hanging in our house, so bad parenting there. And we now have a 2-month-old son, and there's no pictures of him anywhere aside from our phones. So great parenting. All right, so here's the Fourier series. Okay, so let's come down here. I'm going to put n back to 0. All right, so this, we're going to look at the sine series just from 0 to pi, and sorry for the awful herky-jerkiness of this. I hope you don't get motion sickness. So here's what we're going to get. Whoops, I don't have it turned on. Okay, so with, sorry, n is equal to 0. All right, so this is what we get. Okay, and so it looks like we're going up to pi. And notice again the artifacts that we get around pi. We get these more and more wiggles, but the amplitude of the wiggles, as n gets bigger, the amplitudes get smaller and smaller and smaller. So we get something like this. Okay, so the amplitudes are getting smaller and smaller and smaller, like that. Okay, And eventually it's going to be equal to x from 0 to pi, and then equal to 0 at pi. Okay, and then if you look at the odd extension to minus pi, this is what we get. Okay, let me go back down to something like this. Okay, this is what we get. N is equal to 8. And then if I look, let's say, minus 7 pi to 7 pi. Sorry, if I look minus 7 pi to 7 pi, again, we're going to get this function from minus pi to pi, just copy and paste it all along. Okay, now let's look at the cosine. So this is going to be the cosine series. And we're going to start off by looking at 0 to pi. Going to set this back down. 0 to pi. Okay, and now what's going to happen, see if you can make an observation as I move in. See if you can make an observation comparing the cosine series to the sine series. Okay, we're going to get something like this. If I look at minus pi to pi, we'll get the even reflection, which will converge to the absolute value of x from minus pi to pi. And then as I go from, let's say, minus 7 pi to 7 pi, you get something like this. Okay, and notice that even like, once we're at n is equal to 6, this is a pretty good approximation to what it should be. We see some rounding there at pi, and down there at the 0 and the 2 pi and so on and so forth, but it's pretty close. I bet if we get up to 7, see, when we're already up to like, well, anyways, okay. So the point is, we have a very good approximation. Let me get up to n is equal to 10. This is a very good approximation for cosine, and we've only taken 10 terms. Now let's look at sine. Okay, so sine is still not a very good approximation. I mean, at least compared to cosine, it's not a very good approximation. Okay, now I'm going to explain why this is in just a moment, or give it in two. I'm going to explain part of the answer, and we'll talk more about it later. But just think for a moment why that is, based on the formula for the coefficients. Okay, so if you look at the formula for the coefficients, making sure I'm not stepping on cables. If you look at the formula for the coefficients, notice that the BKs only converge like 1 over k. But the AKs, that is the coefficients for the cosines, converge like 1 over k squared. So we have faster convergence with the cosine series than the sine series. And so the question is, why is that? Is that just something that's going on for this particular problem? Is it more fundamental? Stuff like that. And those questions about convergence are some of the things that we're going to touch on later this week, and maybe a little bit next week as well. But okay, that's it for this video. We're going to, I think in the next video, we're going to look at some takeaways from what we've just seen, give some technical definitions, and then in the following video, we're going to look at a theorem that talks about the convergence of Fourier series, and in what sense they converge. Okay, so that's it for this video.